right, in this example, we're going to go back to permutations, and we're going to look at the permutations of the set 1, 2, 3. So we're looking at the compositions of all these, so let's figure out the Cayley table. Well, first in my Cayley table, I'm going to have my permutations. I need to know what those are. So permutation 1, I'm going to write this in cyclic notation. We could have that all of them are separate. 1 goes to 1, 2 goes to 2, 3 goes to 3. Permutation 2, I could still have 1 goes to 1, but then 2 could map to 3 and vice versa. So now I'm not going to write my 1 because that's assumed to be there. Permutation 3, this time I could fix my 3 going to 3, and I could have 1 mapping to 2 and 2 mapping to 1. Permutation 4, we could have 1 maps to 2 and 2 maps to 3, 3 maps to 1. Permutation 5, 1 could map to 3, could map to 2. Permutation 6, we haven't left 2 by itself, so we could have 1 mapping to 3. All right, so now if I look at my compositions of permutations, if we combine permutation 1 with permutation 1, well, this is my identity. So of course that's going to leave me permutation 1. I'm going to leave you to figure out the Cayley table, so you should pause your video and do that yourself. I've figured it out already, and so I'm just going to paste it here. Wow, that's really big. So let's shrink it down. Okay, so we've got our permutation Cayley table. All right, so now I want to look at my subgroup H over the permutations. So now I've got H being P1, P3. So I want to find the partitions of S3. So I want to find the partitions of my set. So all of this is making my set of all my different, my set of 6 permutations. And I want to partition the set into left and right cosets. So let's start with our left cosets. So our left cosets, that's going to be XH. So that's going to be X composed with H. So we're going to have all of our values of X. So that's going to be P1, 2, 3, 4, 5, and 6. And then we're going to have H, which is just P1 and P2. Okay, so when I combine for a left cosset, what I'm looking for in my Cayley table is unique rows. So I can just copy from my Cayley table over here. P1, P1 is P1. I think that I wrote this down wrong. H is supposed to be P3. All right, so P1, P3 is P3. Of course, P1 is the identity, so I can fill this in all the way. All right, so now I want to look for also my values from P3. So P3, P2 is P5, and then P1, 6, 2, and 4. So for my different left cosets, what I'm looking for is unique rows. That was similar to what we did up here. So again, this row wasn't unique, so we could exclude that. So now we're looking for our unique rows here. So we've got P1, P3, P3, P1. So one of my left cosets is going to be the P1, P3 group. I could call that the same as P1H, or I could call that the same as P3H. So I've got different ways to define that cosset. So let's highlight this one. Okay, so that one we could define as P1H or P3H, or it's also the group H. We could also identify it by its permutations, P1, P3. Right, let's look for another unique combination, P2, 5, P5, P2. All right, so again, we've got we could define this in the similar way as P2H or P5H or P2, P5. All right, last one, we could look at 4 and 6. Okay, so P4H, P6H, which is the same as P4 and P6. So notice we've now covered all 6 of our permutations. So we could say that our left cosets that define our set, or partition our set, there's the word I was looking for, are any combination of these. So we could say that one partition are H, P2H, P4H. Or we could say any of the other combinations. We could call that first one P1H, the next one P5H, and then we could stick with P4H. So as long as your combination covers, fully partitions the set, I lost an H over here, then we've got all of our partitions. So now let's look for our right partitions, our right cosets, sorry. So in this case, we're going to have Hx. So now we're going to have P1, P3. And then up here, we're going to have our original permutations. So again, we've got our identity. And now we need to look at our table to copy down 3, 6, 1, 5. And then 4 and 2. So now we're looking for unique columns. I see my, let's start again with yellow, P1, P3. So that one's the same. So we could call that, now we've got our H first, so HP1, HP3. Of course, that's also just the same as H, P1, P3. That's a comma. Let's make it more comma-like. All right, now I want to look for another one. So I see 2 and 6, and 6 and 2. So notice this time our orange is different. This is HP2 or HP6, P2, comma, P6. And that leaves the last one, 4 and 5. So HP4, HP5, P4, and P5. So again, our set is fully partitioned, but now our partitions, so we could say H, HP2, HP4. So that one looks the same, but we could say H and then HP6. And so let me try and make it look different from here. If we had HP5, we would not also have HP4. So HP4 and HP5, those are the same, so they're not going to appear twice in these partitions. So our left and right cosets do not create the same partitions in this case, and that makes sense because it's not an Abelian group. Yeah, so we don't have a property of commutativity. So in this case, our partitions are different, and those are left and right cosets and how they partition things.